This video goes over topics from Chapter 1, Chemical Measurements and Calculations in the textbook, and is preparation for our class number 4. In this video, we're going to talk about Section 1.2 in the textbook, which has to do with chemical concentrations, and we're going to review the topics of molarity, introduce the topic of molality, also talk about percent by weight, percent by volume, parts per million ppm, and ppb, parts per billion. We'll also go over sections 1-3, which is about preparing solutions and how to prepare solutions by dissolving solids or by diluting more concentrated solutions. So first off, a review of what a solution is. So technically a solution is any homogeneous mixture. So that's an important term. Remember, homogeneous means uniform, same top, bottom, left, right, all that kind of thing. Often we think of liquids as being solutions, but solutions can also be gases or solids. So technically air, which is a mixture of nitrogen, oxygen, argon, and some other more minor components, that would technically be a solution. Similarly, certain kinds of metallic alloys, which have variable compositions of the metals that make them up, are kind of like solid solutions. Recall, a crucial characteristic of a mixture is that they have variable composition. So a couple of other pieces of terminology. So the solvent is always going to be the major component. Whatever substance it is that you have the most of, we're going to call that the solvent. The solutes then will be all the minor components. So for example, NaClAq, remember aqueous means dissolved in water. So in this case, water would be the major component. So water would be the solvent. NaCl would be the solute. Now just a reminder, technically because NaCl is one of those strong electrolytes, being a soluble ionic compound, the actual solute will be the sodium and chloride ions that are floating around in the solution. So you can talk about the concentration of sodium cations and the concentration of chloride anions separately, even though in this case they're going to be the same. Alright, concentration then. Because solutions are mixtures and they have a variable composition, we have to define the composition of the solution, even if we're talking about the same solution. So air does not always have the same composition because it might have a variable amount of carbon dioxide in it, a variable amount of water vapor. Similarly, coffee, for example, is not the same solution every time. Some like a light brew, some like a dark brew, some add cream, some add sugar, all that kind of thing. So we have to define for every solute, everything that's dissolved in our solution, we have to define a concentration. We have to say something about the composition. So that's what concentration does. It tells us about the composition of the solution. What is it made out of? So how do we do that? Well, typically we express concentration as a ratio. And we have a ratio of some amount, so I put that in quotes because we can use different quantities to represent that amount. So a ratio of the amount of solute to the amount of total solution. Sometimes we do express that ratio as the amount of solute to the amount of solvent, but typically we use solute to total solution. So it's kind of a ratio of a part, the solution, to the whole, the solute, to the whole, which is the solution. Also a reminder that concentration is what we call an intensive property, so it doesn't depend on the amount that you have. So mass would be an extensive property because it does depend on how much you have. Volume would be an extensive property because it depends on how much you have. But concentration, if you've got a homogeneous solution, it doesn't matter whether you look at the top of the solution or the bottom of the solution. The concentration of the solute is the same because we imagine that the little solute particles are sort of evenly distributed throughout the solution. So what are some typical units for concentration? So in this course, and these are pretty common in science, we're going to look at these main ones. So first one is percent composition. We talk about weight percent, abbreviated WT percent, or volume percent, abbreviated VOL percent. Sometimes we will write these equivalently as percent, and then in parentheses we write W/W to indicate that this is a weight percentage, a weight divided by a weight of the solute, divided by the weight of the whole solution, or percent by volume, so the volume of the solute divided by the volume of the whole solution. So weight percent and this percent W/W, those are just synonyms, mean the same thing, different symbols that you will sometimes see. Parts per million is represented by this symbol, ppm, parts per billion by this symbol, ppb. Molarity, which we'll talk about a little more in detail. Well, we're going to talk about all these in a little more detail in a minute. But molarity is moles of solute per liter of solution, and it's given the symbol capital M. Molality is given the symbol lowercase m, which is unfortunate because in physics we use that for mass a lot, but we'll try and keep those straight. So moles of solute per kilogram of solvent is the way that molality is defined. And we'll see that in a little more detail in a minute. But first, let's talk about percent composition. So this is a typical way to describe the concentration of solutions. It's used a lot in science. So weight percent, WT percent, right? So how we calculate a weight percent, because it's a ratio, like I've set up here, of part to whole, the part is going to be the mass of the solute. So we're measuring amount by measuring the mass of the solute. And we're going to divide that by the mass of the total solution, or mixture, whatever it happens to be. And then to make it a percentage, we multiply this by 100, right? So that will convert it into a percentage. Another way of saying percent is we can talk about it as a part per 100. So like if you have a 5% solution, 5 grams of that solution, 5 parts of that solution are the solute, and the 100 is the rest of the whole solution. Sorry, the rest of it would be 95 grams. Volume percent then is going to be the volume of the solute, so we're measuring the amount by volume. And this would be if we're making a solution out of 2 liquids. So suppose we're mixing ethanol and water together. So we're going to take the volume of the solute and divide that by the total volume of the solution, again multiplied by 100 to make that a percentage. So for example, 95 weight percent ethanol contains 95 grams of ethanol for every 100 grams of solution. So in this case, the ethanol is kind of like the solvent because it's going to be the major component, right? Because the other component is just the 5 grams that's left over to give you the 100 grams of solution. But that's how we would make a 95 weight percent ethanol solution. 95 volume percent ethanol contains 95 milliliters of ethanol for every 100 milliliters of solution. So those might be different, right? Because the density of ethanol will be a little bit different. So 95 grams of ethanol is maybe not the same as 95 milliliters of ethanol. So a 95 weight percent solution is not the same as a 95 volume percent solution. By the way, some of you that may be familiar with adult alcoholic beverages, ethanol is the alcohol that is in adult alcoholic beverages, and sometimes those alcoholic beverages are described by their proof. You know, we talk about 120 proof or something when we're describing an alcoholic beverage. Proof is just twice the volume percent. So 120 proof alcohol, adult alcohol, is going to be 60% by volume ethanol. So if you have 100 milliliters of that alcohol, then 60 milliliters of that sample is actually the ethanol that's in there. So that's a bit about weight percent and volume percent and how we calculate them. So again, it's just a ratio of part to whole, and then we convert those into percentages. Parts per million and parts per billion are really very similar to that, and we can define those in terms of mass or volume. Here I've described them in terms of mass. So first we make the ratio of the mass of the solute divided by the total mass of the whole solution, just like we did for weight percent. But what we're going to do differently is instead of multiplying by 100, we're going to multiply by 1,000,000, 10 to the power 6. So just like weight percents, we could think of those as parts per 100. We're going to think of parts per million as, you know, how many parts there are per million. So if you have 1,000,000 grams of that substance, that solution, and it's a 5 part per million solution, then 5 of those 1,000,000 grams are going to be due to your solute. So we use these when we're talking about very, very dilute solutions, right? So parts per billion, same idea, but we're going to multiply by 1,000,000,000 instead of 1,000,000. So here's a little shortcut. So oftentimes these are used for very dilute solutions. So if the solvent is water, and they're very dilute, then the density of that solution is pretty close to the density of water, which is 1 gram per milliliter. In that case, parts per million is the same as milligrams of solute per liter of solution, or micrograms of solute per milliliter of solution. So these are equivalent units, and they would be equivalent to 1 part per million. 1 part per million is 1 milligram of solute per liter of solution, or 1 microgram of solute per milliliter of solution. There's an equivalent shortcut for parts per billion. You just have to decrease all the powers by 1,000, right? So instead of ppb, instead of being milligrams, per liter, it would be micrograms per milliliter, or nanograms per milliliter, right? So we just changed that number there by 1,000. So change that metric prefix. So we go from milli to micro, and we go from micro to nano. Just to kind of clarify what these definitions are, an aqueous solution that is 1,000 parts per million copper. So Harris uses sort of a European convention sometimes by leaving a space here instead of a comma like we often do. So sometimes in certain other countries, the comma represents a decimal point. Here in the US, we use the decimal point to separate anyway. So sometimes you will see spaces between the numbers just to help represent every 1,000 places. So 1,000 parts per million in copper, what does that mean? It means that we have 1,000 milligrams of copper in every liter of solution. So just following this convention. So 1,000 ppm, that would mean that we have 1,000 what? 1,000 milligrams of what? Of copper in what? Per liter of solution. It also contains, if we just had a milliliter of that solution, we would have 1,000 micrograms in 1 milliliter of that solution. So that's a useful shortcut in thinking about those solutions and making conversions between units, which we'll see in a bit. So let's review molarity and introduce this idea of molality. So first off, we're going to talk about molarity. So molarity then, ratio of part to whole. The part is going to be moles of solute. So instead of talking about grams, we're going to talk about moles of solute. And we're going to divide that by volume, but volume in liters, so total liters of solution. So this is particularly useful in chemistry because oftentimes we like to count particles in moles, and oftentimes in labs we deal in liters and milliliters as our measure of volume. So this ratio is particularly useful. Again, molarity is given the symbol capital M, and so whenever you see capital M, you can substitute in your head that it is moles per liter. Moles of solute for every 1 liter of solution. Equivalently, we can put a metric prefix here, milli, so we can talk about millimoles per milliliter. And this is useful because in lab we often measure things in milliliters, not liters, and so we can use the same molarity unit to represent millimoles per milliliter. These two sides of the equation are equivalent, right? There's an equal sign here because we could cancel out the milli unit, and then it would still be moles per liter, right? So we just sort of like multiplied by 1. You could think of it that way with these units. So millimoles per milliliter also is the molarity unit. This is probably the most common concentration unit in chemistry. How do we use it? Well, it's a great way to convert between liters of solution and moles of solute, or equivalently between milliliters of solution and millimoles of solute. So molarity is our conversion factor. Remember, conversion factors are ratios, moles per liter. We can write them this way. We can also invert that ratio and write them as liters per mole if we need to figure out milliliters knowing moles. All right? So we can go from moles to liters or liters to moles. Liters of solution to moles of solute. Notice that this is different than like a density kind of thing because we're going from moles of what? Solute to liters of what? Total solution. So you have to have all that in the label. So moles of the solute, the stuff that's dissolved, to the liters of total solution. So let's do a quick example here. How many moles of sodium chloride are there in 50 milliliters of a 0.123 molar sodium chloride, an aqueous sodium chloride solution? So the first thing that we're going to do is convert milliliters of solution into millimoles of sodium chloride using molarity. So we're going to use this definition, right? So we're starting off with milliliters. How much do we have? We have 50, right? We want to get the milliliter unit to cancel, so the milliliters needs to go downstairs, millimoles upstairs. So 0.123 molar means 0.123 millimoles of the solute, sodium chloride, for every 1 milliliter of solution, right? So millimoles per milliliter is the same as molarity. So then you see that our milliliter unit will cancel out and we're left with millimoles. So 6.15 millimoles of sodium chloride. Then our question was asking how many moles of sodium chloride are there. So now what we're going to do is convert millimoles into moles just using our metric prefix. So what we do is we just replace the milli with its power of 10, so that's 10 to the power minus 3, and there we've converted into moles. Simple and easy. 6.15 times 10 to the minus third moles. So you're probably wondering what this picture is. Well, this is bad chemistry joke time. So what do you call a tooth sitting in a glass of water? why that's a 1 molar solution. Let's talk about molality. So molality is a little bit different. Again, it's still moles of solute, but what we're going to do is divide it not by the whole solution, but by a weight, the kilograms of the solvent. So this is the ratio of solute to solvent. And so molality, this unit, lowercase m, represents moles per for every kilogram. So for every kilogram of solvent, how many moles is dissolved in that 1 kilogram of solvent? So when do we use this? Well, this is typically used for precise work. So because it's a ratio of moles per kilogram, molality does not change with temperature because moles and kilograms won't change with temperature. If we go back and look at the definition for molarity, you see that we've got liters of solution down here. So it turns out that as you heat and cool substances, they tend to expand and contract, right? A solution will do that too. So a hotter solution will, even though it's the same solution, will expand a little bit, and so the total liters of solution will increase just by a little bit, but it's enough to change the molarity in really precise work. So instead of that, we use something that is insensitive to temperature. So kilograms do not change, moles do not change, so that doesn't change with temperature. So molality. So when we're talking about molality units, I've referred to this is our 1 molar solution. What do you say for molality? Well, again, that's just going to be without the ity at the end. So we talk about a 1 molal solution, or a 0.123 molal solution. So that would be 0.123 moles of solute dissolved in a kilogram of water. So that's what that would mean. All right, so let's now move on and talk about section 1-3. So this is about making solutions. So we're going to look at some examples of how you would make solutions using some of these definitions. So first we want to figure out how much copper 2 chloride pentahydrate. So this is a solid crystalline material. You can get it as a solid crystalline material. You could also mix this up in water and then you would have a solution. So how much of this stuff is needed to make 500 milliliters? So that's how much of the solution we want to make. And we, the experimenters, will always get to decide how much we make for our particular experiment, right? How much are we going to need, right? So don't make more than you need because that's chemical waste, but make sure you make more than enough in case there are mistakes. And we want this solution to have a concentration of 1000.0 ppm in copper. So that means the amount of copper here, that we would have 1,000 grams of copper in every million grams of this solution. Okay, so if we had 1,000,000 grams of this solution, which would be a lot, then inside there would be 1,000 grams of copper. So we're going to look at making this solution in 2 ways. First, from the solid. So I told you that this is a crystalline material, nice blue crystalline material that we can order as a solid chemical. And so we might want to weigh that out. So how many grams do we need to weigh out? And then by dilution, another way that we could make this solution, let's say that we had a solution that was already 10,000 parts per million in copper, right? So we already had copper dissolved in that solution. What would we do to dilute that solution down to make 1,000 ppm solution? So the way that we make solutions precisely and accurately is we use this device called a volumetric flask. We'll be using these in lab this week. But these are used to contain a fixed volume. So for example, if we're measuring out the solid, what we would do is weigh out a certain number of grams that are going to get us to this ppm value. We would add all of that quantitatively to the flask. So that usually means that whatever we weighed it in, like a little weighing boat, we would then rinse that weighing boat out really well with our squirt bottle of distilled water. So that way every last microscopic speck gets dissolved and rinsed into this flask. We would also want to rinse down any bits of the powder that were in the neck of this flask, or if we used a funnel to help with the transfer, we need to make sure we rinse the funnel well. Anyway, so then we would have the solid down here with perhaps some water. We would add some more water, maybe up to here, swirl it really well to get all that solid dissolved, and then add water up to this mark, and then we know we would have precisely 500 milliliters of total solution. If we were doing this by dilution, then what we need to do is transfer some volume of this solution. So we put a certain number of milliliters of this more concentrated solution in here and add water up to the mark to dilute it down to the 1,000 parts per million. Okay, so let's talk about dissolving the solid first. All right, so we need to figure out how many grams of copper 2 chloride pentahydrate are needed to make 500 milliliters of a solution that is 1,000 parts per million in copper. So just a note, the formula weight, so that's the kind of like the molar mass, but it's the molar mass for one formula unit of this ionic compound, is this number. So 224.53 grams per mole, calculated off the periodic table. So first what we're going to do is figure out how many grams of copper we would need. We're going to use this little trick that 1,000 parts per million in copper is going to be the same as 1,000 micrograms per milliliter. So we're just going to replace ppm with micrograms per milliliter. And then we want to make a 500 milliliter solution. So how many micrograms of copper is that going to be? So we can use this as a conversion factor, the 1,000 parts per million as a conversion factor to go between micrograms and milliliters, right? So this is micrograms of the solute and milliliters of the solution. And so this acts like a conversion factor. And we write it this way so that milliliters is in the denominator so that it will cancel the milliliters that's here. And we end up with micrograms of copper. So now we know how many micrograms of copper we need. But we're not getting the copper from just pure copper. We're getting it from this substance. And so we're going to have a higher mass, right, because we need all of this substance. So we need 5.0 times 10 to the 5th micrograms. So let's first figure out how many grams that is. And the way we do that is we simply replace this micro unit with its power of 10. So we've got 5.0 times 10 to the 5th. That's the number we were starting out with. We replace the micro. We get 10 to the power negative 6. And when we multiply 10 to the power 5 times 10 to the power minus 6, you might remember this rule from math that what we do is we just add the exponents. So 5 plus a negative 6 is a negative 1. So there we go. We need 0.5 times 10 to the minus 1 gram. So that's the same as 0.5 grams of copper. That's how much copper we're going to have in this solution. But we get the copper from this compound. So the second step is to figure out how many grams of this whole compound we need. All right, so first we need to convert the grams into moles because we have to count, right? Because this formula is giving us a count. It tells us there's one copper atom in every one of these formula units. So we first need to convert into that counting unit. So we're going to use molar mass to do that. So 5.0 times 10 to the minus 1 grams of copper. And so now we need the molar mass of copper, right? So we're given the molar mass of this substance, but we need copper. So we look that up off the periodic table. It's this number. We put the mass in the denominator because we want the gram unit to cancel out. Then we will know, after we're done with this multiplication and division, how many moles of copper we have. So now we're going to do what is kind of a silly step, but it converts our units correctly. So we're just going to multiply by 1. And so that's because in this formula, we have one copper atom for every one formula unit. So if we had a mole of these formula units, we'd have a mole of copper atoms, right? So we can say that there's 1 mole of these formula units for every 1 mole of the copper. And now the moles of copper unit will cancel out, and we have figured out how many moles of copper 2 chloride pentahydrate we have. And then the last step is to figure out how many grams that would be, right? So now we're going from moles to grams. And here is that conversion factor. So that's just using the molar mass. We want moles to cancel out, so we make sure that that's in the denominator. And we're looking for grams. That needs to go upstairs. So the moles cancel out. We end up with grams. And when we multiply this all together, we get this number, 1.7667 grams. So that's out to 4 decimal places. We've got 4 decimal places in this number. We're trying to make a precise 500 milliliters. So even though it looks like it has 3 significant figures in here, a volumetric flask is probably precise out to the hundredths place. So this is probably like 500.00. So we have a lot of precision, so we want to keep all that in our calculation. All right, so what does this mean in terms of how you would actually mix up this solution? Like if we wanted a recipe, what we would do? Well, we'd want to weigh out 1.7667 grams of that solid copper 2 chloride pentahydrate. And then we would quantitatively transfer, like I described before, to this flask. We would add water, so the flask is about 2/3 full, and swirl to dissolve all the solid, and then add water up to the mark. And then we would put the cap on and turn this flask upside down 20 to 25 times to make sure that the fluid in the neck has been mixed with the rest of the solution really well, to mix that really well. And then we would have a solution that's 1,000 parts per million in copper. So that's how we would make up that solution. So we have to go through some steps to come up with the recipe for how to do this. Now this is a real common task in a lot of scientific fields, mixing up a solution to a known concentration. So this is important that you practice and learn how to do this well. Now in practice, it's very hard to weigh out exactly this number of grams. So what we do is try to weigh close to this number of grams and then record what we actually measured. And then we would go back and sort of run this calculation backwards so that we would figure out what our actual parts per million is. So we were trying to make 1,000 part per million in copper solution. It's probably not important that it's exactly 1,000, but it's probably important that we do know exactly what it is. So maybe it turns out to be 1,007 parts per million or 995 parts per million, right? So those would still probably be okay concentrations. And that's easier to measure out than trying to get exactly down here, because this decimal place is like a speck of dust. It's just a tiny amount to change that decimal place. It'd be really hard to measure that out. So now we're ready to try to make a solution by dilution. So how do we do that? Well, we have this very useful equation that's called, ironically enough, the dilution equation, right? So to calculate quantities of reagents to prepare dilution, we use the dilution equation. And what that does is it equates information about the more concentrated solution that we're diluting to the dilute solution that we're trying to make, okay? So C is the concentration. The subscript here, CONC, means that it's referring to the concentration of the more concentrated solution. This is the volume of the more concentrated solution. This again is the concentration of the diluted solution. This is the volume of the diluted solution, okay? So what we're doing when we're using this equation, we need to make sure we have the same units for concentration on both sides. So they could be molarity, but they could also be molality or parts per million or whatever. Volume, again, we need to have the same unit. So milliliters on both sides, liters on both sides, whatever. So what's going on here is that when we multiply concentration by the volume, we get an amount of solute when we do that. And what we're saying is that the amount of solute that we get from the concentrated solution is equal to the amount of that solute that we've put into the dilute solution, okay? The only difference is that we're adding more water, so we're going to change the concentration. But we're going to take a certain number of moles or a certain number of grams from the concentrated solution. That's going to go into our flask, right? And then we're going to add water to that flask. So that's how that works. And so you just plug in the three variables that you know and solve for the variable that you don't know. So if you're diluting a solution, this is a way to calculate the dilution. Or if you're trying to do what we're doing now by finding a recipe, we're trying to find what volume of the concentrated solution to measure out. So that's how that works. So how many milliliters of 1,000 part per million copper solution are needed to make 500 milliliters of a solution that's 1,000 parts per million in copper? So we want to figure out how many milliliters of the copper to chloride pentahydrate solution to take. Okay, so this is a solution that we know is 10,000 parts per million in copper. So the concentration of the concentrated solution, 10,000 parts per million. The volume of the concentrated solution, that's what we're trying to figure out. The concentration of the dilute solution, we want to make a solution that's 1,000 parts per million in copper. So that's less than our concentrated solution. And the volume of the dilute solution, well, we want to make 500 milliliters because we think that's how much we're going to need for our experiment. So we've got one unknown in this equation. And so we solve this equation by dividing both sides by 10,000. So we have 1,000 times 500 divided by 10,000. The ppm unit cancels out. We're left with milliliters. And so it says 50 milliliters. So what we're going to do is measure out with, say, a pipette, a 50 ml pipette. We're going to measure out 50 milliliters of this solution, put it into this flask, add water up to the mark, and mix well. All right, sometimes it's useful to convert between concentration units. So they all mean the same thing, right? A solution only has one concentration, but the number in molarity or molality or parts per million or parts per billion will be different. And so maybe we want to convert between those. So in order to do that, we're going to need to make use of density, because molality and molarity are talking about the total volume of solution, whereas parts per million and parts per billion and percent sometimes are talking about the total mass of the solution. So density then can be our conversion factor to go between mass and volume. So if we know the volume of the solution and want to know the mass of the solution, we can do that by using density of the solution as our conversion factor. Just a reminder that concentrations are intensive properties, so they don't depend on the amount of solution. So oftentimes when we're talking about concentrations and converting between the units, we won't be told how much solution we have. Turns out it doesn't matter because this is an intensive property. So one of the steps in converting is we will sometimes begin by assuming that we have a certain amount of solution because we weren't told, but because it's intensive it doesn't matter. So we're going to pick an amount of solution that makes our calculations easy. So for example, if we're dealing with molarity, we might pick 1 liter, right? Because then we know exactly what the number of moles are. If we're dealing with a percent by weight, we might choose 100 grams. If we're working with parts per million, we might choose 1,000,000 grams as the amount of solution that we have. And then what we're going to do is we're going to use the density of the solution to convert between mass and volume of solution. So we'll use the density to interconvert mass and volume, whichever way we need to go. So from volume to mass if we're going from molarity to percent weight, or from mass to volume if we're going from percent weight to molarity. And then we will use molar mass to interconvert between grams and moles. So maybe we need to know grams of solute, and so we would convert from moles of solute. Then we use the moles of solute and the volume liters of solution to find molarity, or use grams of solute and grams of solution to find percent, parts per million, or parts per billion. Alright, so let's finish up this video with a quick example. So we're going to work this example, and I'm going to switch over to my Blackboard and actually work through this problem in real time so we can sort of think about all the steps. So let's go over to the Blackboard. Let's work through this problem. I'm going to work through it and kind of talk aloud as I'm solving this problem so that you can get an idea of how we might go about solving this problem. So I may not take the most efficient direct route. We may hit some dead ends here and there, but we'll work our way through it. The idea is to give you an example of a problem-solving strategy. So one of the first things that I do when I encounter a problem is I write down all the stuff that's known, and then I write down, to make sure that I know what I'm looking for, you know, something right here. So I want to know the parts per million of sucrose in this solution. Right, so stuff I know the molarity of the sucrose solution, I know the density of the solution, SOLN is my abbreviation for solution, I know the molar mass of sucrose, and I'm looking for parts per million. So oftentimes when I'm looking for a particular quantity, I'll write down a formula that would let me calculate that quantity. So let's do the formula first. So to figure out parts per million of sucrose, what I would need to know is the grams of sucrose. I would need to divide that by the grams of solution that we have, and then I would need to multiply that by 10 to the power 6 to get parts per million. So it looks like somehow I'm going to have to figure out grams of sucrose and grams of solution to figure this out. So I haven't been told how much solution I have, but we learned in that last step that it doesn't matter how much I have. I can assume any amount that I need that would make the calculation easy. And just to remind myself, this 2.55 molar, that means that I've got 2.55 times 10 to the negative 5th moles of sucrose. Sucrose, by the way, is just ordinary table sugar, so there's a little chemical factoid for you. Divided by 1 liter of solution. So that's what the molarity of sucrose is, so that number. So if I think about this bit right here and this bit right here, it looks kind of like what I'm going to need to do is go from moles of sucrose in the numerator there, so I'll just abbreviate that suc, yeah, so moles of suc, to grams of sucrose, suc, there we go. All right, so moles of suc to grams of suc, so we're going to have to convert that in the numerator, and then in the denominator it looks like I have to go between liters of solution to grams of solution. All right, so we know how to do this first conversion, right? That uses molar mass, and we actually know how to do the second solution conversion because that's just going to involve the density, okay? Good, so in this example, it might be helpful if I simply assume that I have maybe a liter of solution. So let's do that. Let's assume, because I'm given molarity, right? And molarity is moles per liter. So let's assume that we have this volume. And again, what we're trying to do is find the bit to go in the numerator, the bit to go in the denominator, and then I could do this calculation and find ppm. So that's the strategy. So let's assume that we have 1 liter of solution. And if we have 1 liter of solution, that means that we have 2.55 times 10 to the negative 5th moles of sucrose, right? Just from the definition of molarity. So that made that calculation easy. And now I just need to do this calculation, the moles of sucrose to grams of sucrose. So let's go ahead and do that. So I'll just write a conversion factor here as a set of open parentheses with an empty little horizontal slash. And so we want to cancel out the moles of sucrose, so that needs to go downstairs, moles of suc. And then we need to know the grams of suc, that goes upstairs. All right, so that's just this number right here. So next to the gram unit is the 342.30. That's the number, the factor that's next to this label gram. And what's next to the label of the mole unit? Well, it's a number that's implied, 1 there. And so the moles of sucrose will cancel out. And from that, then I'll be able to calculate that value. So I'm just going to punch that into my calculator, do the multiplication there. I get 0.008729. I'm going to keep all the digits in my calculator for later when I do this calculation. But here I had 3 significant figures. Here I have more than that. So I want to make sure that in my calculations, I keep at least one more digit, one more significant figure than I have, and then I'll round at the end. This way I don't have rounding errors in the middle. So record it to at least one more significant figure, maybe even more than that. So there we go. And so that's how many grams of sucrose I would have in 1 liter of this solution. So I figured that bit out. So now I know what's going to go up here in the numerator of this calculation. So this is the formula that I need to calculate ppms. I need to know grams of sucrose. Well, I do now. Yay. All right, so let's keep on going. We're going to scroll down here a little bit, give us some more room. Now I need to do this next bit where I go from liters of solution to grams of solution. So I've assumed that I have 1 liter of solution, right? 1 liter of solution, and I want to convert that into grams. So to do that, I need to use the density. But the density is in units of grams per milliliter. But I know how to convert from liters into milliliters and stuff using metric prefixes. So up here I'm going to say that I have 1 gram of solution, right? That's the total solution, for every 1, and milli means times 10 to the negative 3rd liters. And so now my liters of solution will cancel out, and I end up with 1,000 grams of solution. Okay, so now we're ready to, we now know the mass in the denominator here. So now I'm ready to solve the problem by plugging into my equation right there. So let's do that. ppms equal to grams of solute, so 0.008729 grams of sucrose divided by the mass of the whole solution. So I have 1,000 grams of solution because I assumed that I have 1 liter. And then to get parts per million, I need to multiply by 1,000,000 at the end. So now we can just punch all those numbers into our calculator and see what we get. And so I ended up with a nice round number here. So we're going to round that to 3 significant figures because that's what we had in our molarity to begin with. So that's 8.7, and then I have 2.865 in my calculator, so I'm going to round the 2 up because the 8 that comes after it is bigger than 5. So I'm going to round that to 8.73 parts per million sucrose. And there we have it. So we have converted from a molarity to the equivalent part per million unit. Now remember, this is the same solution, same sucrose solution, has the same concentration, we're just expressing it in different units. So 8.73 parts per million is the same thing as 2.55 times 10 to the minus 5 molar. So you see why parts per million is kind of a useful unit because it gives us kind of nice numbers when we're talking about really dilute solutions like 10 to the minus 5. All right, so there's how we work an example of that conversion problem. You should be able to think about how we would work this problem backwards to convert from parts per million to molarity, or if we had parts per billion to molarity, or those sorts of things. So it gets a little more complicated when we're talking about converting to molality, because then you're going to have to take the total mass of the solution, subtract off the mass of the solute to get the mass of the solvent. So there's an extra step in there that'll make that one a little bit more complicated. Okay, so that's it for this problem. I'll see you in class.